All right, in this video, we're going to talk about Doppler. We're going to talk about Doppler effect. And hopefully we're going to come across the equations that allow you to work out how the frequency changes of something when it's either moving away from you or moving towards you. Okay, so you may have recognized this like on the road, like when you're walking by, usually in an ambulance or a police car, whirs by, and you hear that characteristic really that kind of noise. And the idea is that it starts off with a really high pitch and then goes to a low pitch as it moves away from you. So it starts getting higher and it's higher and higher, and then it gets lower and lower. And we're going to hopefully explain that effect based on this idea of Doppler effect. So Doppler effect is not just only in sound, it's actually observed in light as well, but we won't come across the light side of it until we study some astronomy. When we look at something called redshift, which is, it has different implications, but the general physics idea, because of them being treated as waves, is the same. So let's look at a situation here. So we've got, say we've got an object, so like a car. So I'm going to draw a really bad looking car, so I apologize for this. And that car is moving towards you in that direction. Sorry, that looks like the front, and that looks like the back, but there's a car, it doesn't matter. And the problem is that this car is honking its horn, for example, and so as a result, the sound it's giving off sound waves. I'm just going to throw 3 sound waves. Now, for the purposes of this diagram, these should be equally distanced because the wavelength is the same, okay, and the frequency is the same. But when this object is now moving, so this is what it looks like when it's stationary. Okay, so what does it look like when it's moving? So what does it look like when it's moving? So let's redraw my car. So the effect of the car moving now, so it wasn't really moving, so I should scribble that out. So it's stationary over here, but now it's moving. Let's see how this looks different when the car is moving. So when the car is moving, what we end up having is a bunching effect in the direction of motion, okay? So we might have something like this. Okay, and you can see here that the effect of moving has caused these wavelengths to decrease. Well, what happens, hopefully you remember, when wavelength decreases, the frequency increases, and hence why we hear a more higher pitched noise. So this will appear higher pitched than what you heard over here, because the wavelength has decreased, the frequency has increased. So let's just say that. So the frequency has increased and the wavelength has decreased. The same could be true about what's happening over here, that the wavelength has gotten further apart. So the effect of that, so say for example, now you're stood on the other side of the car or ambulance going away from you, the effect is that the waves have become more spread out as a result of the object's motion. So we can say that it's a lower pitch sound that as a result of a lower frequency, but this time a higher wavelength. And so this is the general principle around Doppler effect, and trying to get your head around why we hear these changes when something is moving towards you and when something is moving away from you as a result of the changing wavelength and hence frequency of that object. So let's have a look at explaining what's going on in each of these situations. We'll start with the getting higher situation because it's useful to see. So I'm going to remove that from under there because otherwise I'll bring that back on when it's needed. So what happens is we've got this situation where the wavelength has been decreased when it's moving towards you. Okay, so just a reminder, so the wavelength has decreased when it's moving towards you. And we need some sort of term to indicate how much that wavelength has decreased when it is moving towards you.
So think about how much the wavelength has decreased in terms of a useful amount of time. Well, we know that from the equation velocity equals distance over time, that, that we could, in an amount of time that was relevant to the wave, so let's say, for example, the time period, okay, so the time period in one time period of this wave, based on the velocity of the object, this distance here is the extra distance covered, or effectively the distance that is taken from the lambda, or from the wavelength, which is an important point to consider, because we can now rearrange that and say that the change in lambda, okay, the change in wavelength, or the reduction in wavelength, in this case, it's going to very specifically be a negative reduction, because obviously we're talking about the wavelength shrinking, is that we could rewrite this equation based on that. So we can actually say that the amount by which it's decreased is the velocity of the object, okay, is the velocity of the object times by the time for the time period. Okay, so it's very, very pertinent to kind of note down that this is the loss of wavelength here, and for the purposes of our little derivation that we're doing here. So what can I do with this? Well, I can write a term to say that the original wavelength minus this term VST, the time period, is going to be equal to kind of like a new wavelength. Okay, so like equals a new wavelength, a new lambda. Okay, so that gives us an idea of what the new wavelength of this sound is, and then effectively you could work out, if you knew what the new wavelength is and you knew what the speed of sound is, you could work out the new frequency, which is related to what you actually hear. So let's see if we can actually come up with a term for the new frequency, or the observed frequency, to allow us to work that out. So think about it very carefully. So using the equation V is equal to F lambda, okay, sorry, I put that a bit high. V is equal to F lambda, then F will be equal to V over lambda. And so for the purposes of this is now the speed of sound. So bear in mind that this is the speed of sound. Okay, so that's the speed of sound. And then what we can then do is write in a change here for what is the observed frequency. Now, how does that change? Well, because the observed frequency has a different wavelength, and we have a term for our new wavelength, so we can put that in there. F naught is equal to V over lambda minus VST. Okay, so just bear in mind that this is the original lambda, okay? This is the original lambda. That's the lambda that is effectively emitted as the sound that we're interested in there. So this is the observed frequency, speed of sound, the amount by which the wavelength has changed. Now we've got kind of a lot of different terms going on here, so we actually want to rewrite a lot of these terms in terms of, to kind of unify the ideas in terms of frequency and velocity. So we really need to be able to get rid of this lambda. We need to be able to get rid of this time. Well, let's look at this equation back up here and just look at the changes we can make. So for Vs over t, we could actually rewrite this as in terms of a frequency, because hopefully you remember that 1 over the time period equals the frequency. And so retrospectively, 1 over the frequency equals the time period. So we can rewrite this equation as Vs over F, or Fs, sorry, which Fs is the frequency of the sound that was emitted, okay? Because remember, this is the frequency of the sound that was emitted. This is the velocity of the object, okay? Let's just be really clear about what these terms are. Vs is the velocity of the object. Fs is the original sound frequency. So we can then put that in there, and we can also rewrite this lambda term, just the normal lambda, as in terms of V and F as well, based on this equation. So we can write that as V over Fs. Now notice how this is different now, because we've got the velocity of the sound. So this is the speed of sound. This is the frequency of the sound. So velocity of sound, frequency of sound that was originally emitted. Remember, this is the wavelength that was originally emitted. So then we can actually put those two equations in place of these two terms here to actually make a new equation, which looks a bit like this. Now, mathematicians are going to freak out a little bit when I write this, but that's okay. Which gives us V over Fs minus Vs over Fs. Now, hopefully you're seeing there's a common denominator here. So I can rewrite that again as V over V minus Vs divided by Fs. Okay, which then you will hopefully see I can rearrange this more to satisfy the mathematicians to be Vfs over V minus Vs. And that equals the observed frequency of the sound that is emitted. So let's put a nice square around that to show that that is actually our Doppler shift equation. Okay. Now, don't worry too much if you can't like follow that through, or you missed a bit. Do go back and watch certain bits that I've explained. I do want to kind of just define these terms over here so that they're nice and clear, because I've said them throughout this derivation, but I've not written them down very specifically. So let's go over here and write them down. So so V is equal to the speed of sound, okay, in the medium that it's in. Now, bear in mind, the speed of sound can change based on any number of factors, like depending on what material you're in. So, for example, if you're underwater, it's much faster, okay? Just as a small example there. So just bear in mind that the speed of sound can change. Then let's look at the other V term. So Vs is the speed of the object. Speed of the object. Now, in the example that I've given you here, the object is moving towards you. Okay, it's moving towards you. That doesn't mean that the object can't be moving away from you, because you could be stood here or you could be stood here. And the equation we've just done is all about what happens if you're stood here. So let's go right through the rest of the terms. So FO, what we're looking for FO is the observed frequency. It's the frequency you observe as the observer of that object moving, okay? Frequency F, normal F, or Fs is the original frequency that's emitted by the object from the source, okay? That's what S stands for. So the source frequency. Okay, let's just make sure I've got all the terms there. Yes, I do. So you've got all of those terms now that you need. You've got V, Fs, source frequency, V, speed of sound, Vs, speed of the source, speed of the object. Okay, that's what S stands for, source. I should probably put source there instead of object, but you get the idea. So that all comes together quite nicely, and hopefully that you'll be able to utilize this equation, hopefully in class. But there's another equation that you need to be aware of about what happens in the second scenario. What happens if it's moving away from you? And it's a very small change. And I'm actually just going to circle that change over here in pink. And the wavelength, instead of being minused, it actually gets bigger. So the small change happens here instead, and it becomes a plus. So let's go back over here. We can actually just rewrite this equation without doing all this algebra, because the only thing has changed is this term all the way down here. Okay, sorry, I'm not writing an equals sign here. I'm just underlining it so you can see it. So in this case, what we've got is we've got F naught is going to be equal to V over V, oh, sorry, Fs, O plus Vs. Okay, so that gives you a new term for what happens if it's moving away from you. And this gives you a term if it's moving towards you. So minus is towards, positive is away. Okay, and then hopefully in class we'll be able to put that together and do some kind of practice calculations on this. Okay, thanks for watching. See you in class.